Okay, everyone, welcome to our third third seminar by our professors. We have today Dr. Jin Zhang. He has received his PhD from UC Berkeley, and he used to work at HP in Japan, which is amazing. And now he's here with us. Thank you so much. He's going to be talking about graph signal processing.
So thank you for the introduction. So I'm a professor here at York. It's my 5th year here. Half of it is on COVID, so I don't get to see a lot of people. I get to see whoever can show up today. So today I'm going to talk about graph signal processing, which is my main topic for the last decade or so. I'll talk about theory and applications. I'm mostly going to talk about high level. I did my best to use as little math as possible, impart intuition instead. So I usually talk about my collaborators and coworkers first. As you know, research is a team sport, so I give credits to all the people, fantastic people I work with. Mike's okay. So postdoc, previous postdoc, grad students, co-supervised students, periodically have visitors from out of town, collaborators, of course, within York, in the States, some industrial collaborators. Folks in Asia, I spend quite a bit of time in Asia, so China, Taiwan, and Japan also. So I'm thankful for all the collaborators. All the work I present today will be in collaboration with all these folks. Very simple outlines. I'll talk about graph signal processing overview, roughly give you an idea what it's about. I'll talk about some of the key topics within GSP, so graph learning, graph filtering, sampling, and some recent work on GSP analysis that would help us inform better design of graph convolutional nets, and then finally conclusion. So I'll start with GSP overview. What is graph signal processing? So in a nutshell, you can think of graph signal processing as traditional frequency analysis that you would take a course like here in 3451, which I teach, signals and systems. You talk about Fourier analysis of discrete signals, right? So discrete Fourier transform, you look at how a signal can be decomposed in low frequencies and high frequencies, etc. Hopefully you recall things that you learned in your first signal processing course. If we combine that with a graph kernel, that signals that now live on irregular kernel described by a graph, you have graph signal processing. So in a nutshell, you can think of graph signal processing as a generalization of spectral analysis tools that you've learned in your undergraduate course and signal processing course. Now you're working on discrete signals that live on graphs. And it's a popular topic within the Signal Processing Society. So I'm from the IEEE Signal Processing Society. That's why I published most of my papers. And now there are textbooks now on this topic. So why is this so interesting? It's that the notion of frequencies can now carry over to data that live on irregular kernels, right? And there are many, many data that live in irregular kernels. You can think of sensor networks. We're measuring temperature or humidity within a forest. It could be a social network where you connect with friends on Facebook, for example. So your signals that live on top of those networks, such as temperature, humidity in the forest, or voting within the last federal election, for example. Those would be signals on the graphs. If you want to analyze the signal using frequency analysis, this is the kind of tools that you would need. So I'll start with some definitions about what do I mean by frequencies on graphs. We're going to define something that's called a Laplacian matrix, which is the degree matrix minus the adjacency matrix. They give a Laplacian matrix. It's called graph Laplacian matrix. Now you do the eigen decomposition of Laplacian matrix. You have a set of eigenvectors and eigenvalues. Then the eigenvalues would be your graph frequencies. Your eigenvectors would be your Fourier modes. I'll illustrate what that means later. It's interesting to know that so the set of Fourier modes will define a graph, what we call graph Fourier transform, which is a generalization of things that you would know on a regular kernel, like discrete cosine transform is actually the graph Fourier transform for a line graph with all the weights 1. Right? Discrete Fourier transform will be like a circle unweighted graph with all the weights 1. So you can think of graph Fourier transform as a generalization or transform that we already know from signal analysis, signal processing courses. So you might be wondering, why do we call these eigenvectors frequency? It's the fact that the zero crossings increase as the eigenvectors associated with larger and larger eigenvalues, right? So for example, you see this is the second eigenvector. The first eigenvector has no zero crossing, it would just be like the constant vector. And then the second eigenvector has 1 zero crossing. And no matter how you change, in this case, a line graph, you change the weight between the first two nodes from 1 to 0.2 and 0.1, and etc. This is essentially telling the graph that the pairwise similarities between the first two samples are getting weaker and weaker relative to the rest of the pairings, right? Then you can see the shape of the second eigenvector started off from discrete cosine, right? So this is like the first, when W12 equals to 1, as I mentioned, it's a line graph, all weights 1. Then the second eigenvector is actually a cosine, that's what you see here. As the weight becomes smaller and smaller, again, you're telling the graph that the relative pairwise similarities become weaker compared to the other pairs. So it is describing the shape of that. And you can see that the difference between the first sample and second sample becomes bigger and bigger as the weight becomes smaller and smaller. But the point here is that no matter what the W12 happens to be, how big or how small it is, this second eigenvector only have one zero crossing, right? It crosses the zero line only once. And you look at the eigenvectors associated with the larger eigenvalues that will cross over more, right? And that agrees on intuition what high frequency is, right? You think of high frequencies as things that go up and down a lot. And that's why we call these things, these eigenvectors, Fourier modes, and that's why I call these eigenvalues a graph frequency. To show you a better illustration of what that means, we constructed a graph. This is the United States. We look at the most populous cities and we connect them with an edge weight that is inverse proportional to the distance, right? So if they're really far apart, you have a small edge weight. If they're really close together, you would say a large edge weight. Again, it's supposed to reflect the pairwise similarities. So if the distance is small, you want a larger edge weights. And as I mentioned, you look at the first eigenvector as the DC component, so there's no zero crossing. Everything is just positive. You look at the first AC component, the second eigenvector. Now you can see that as you go from the west coast to the east coast, the eigenvector goes from negative to positive. So you have some zero crossings in the middle states now. You look at the next eigenvector, this is the third eigenvector. You can see that when you go from the west coast to the mid states to the east coast, you go from negative to positive to negative. You can see there's more zero crossings, right? And then you go into higher and higher frequencies, you see zero and more zero crossings. Again, that agrees with our notion of what high frequency components look like. You have more zero crossings and therefore high frequencies. So with this decomposition, a signal can now become decomposed into different frequency components. You can do frequency analysis like you would do with traditional signal processing. So this is an interesting figure that I've drawn a couple of years back to kind of position how graph signal processing relates to different fields in the computer science, right? Could you mention graphs? One of the most common questions is, well, that's just graph theory. Haven't that been done before? So graph theory actually talks about the structure of graph itself, right? Like you want to find, given a graph structure, what is the shortest path from S to T, for example? What is the Max Vormin-Klett traveling salesman? That's to do with the graph structure itself, right? Again, from signal processing, we're not so much interested in the graph structure, but the signals on top of graph, right? So we're going to propose things like transformer wavelets to process signals on graph. So that's kind of the differentiation. We leverage a lot on spectral graph theory, which studies the eigendecomposition of graph variation operators like graph Laplacian matrix, adjacency matrix. So there's a relationship there. If you look at the machine learning literature, they use a lot of graphical models, such as the Gaussian-Markov random field. And we certainly have a lot of commonalities with machine learning in the sense that we're also dealing with signals on graph. You think of those as random variables, for example. There's a relationship between graph signal processing and machine learning, as well as some of the other fields. So I'm not going to talk about all of them, but this kind of gives you a good dichotomy of how GSP fits in with the rest of computer science that mention the word graphs or something related. So I'll start talking about some of the key topics within graph signal processing. This is certainly not an exhaustive list. It's just some of the topics I've been working on that I find interesting, and hopefully you can find them useful as well. So first, I'm going to talk about graph learning. So obviously, graph is a human construct, right? When you given data, whatever data you have, whether it's images on the internet or sensor data from a sensor network in the forest, for example, there's no graph. So a good question is, what is a good graph, right? What are you trying to capture with the graph? So first of all, graph have nodes and edges, right? So an edge, by definition, can only connect two nodes. There are actually things like hypergraph that actually connects more than two nodes, but let's not worry about that for now. Typically, when you have an edge, it connects two nodes. So you connect two nodes, you want to explain or describe pairwise relationship, right? So that's what we look for. A good graph would accurately capture pairwise relationship. Typically similarities, right? So if you have, here's an example of sensors in forest. If the two locations are very close, for example, and the altitude is about the same, you expect the capture humidity to be similar, right? So you want an edge weight that reflects the similarity. So if there's humidity, you expect the humidity readings to be close, you expect large edge weight, for example. As I mentioned, often you're just given data. So how to find the most appropriate graph from data, we call this graph learning from data. And we have taken two approaches to this, not the only way of doing that, but you can suppose you have a covariance matrix. You can learn a sparse inverse covariance matrix from that efficiently. So that's one we're learning an appropriate graph from data. And there are cases where you don't actually have a covariance matrix, empirical covariance matrix, in which case you might have features per node, you have to compute a feature distance, and then from the feature distance, you compute an edge weight. So I won't have time to talk about the second part, although we spend a lot of energy talking about cases like that, where you cannot compute an empirical covariance matrix a priori, and so you're relying on features, pre-computed features, and then you compute feature distance. So there are some papers that publish on that. You can look that up. I'm mostly going to talk about the first part. So given an empirical covariance matrix, how can you compute a graph Laplacian matrix to describe the conditional correlations? Before I jump into the math, I want to point out that there are graphs that are not so obvious when you think about graphs. For example, sine graphs, right? Most of the graphs you see in the literature, in the GSP literature, and actually other literature like GCN, etc., they usually talk about positive graphs. So the edge weight's usually positive or negative. And because you assume there are pairwise similarities, right? Not dissimilarity. So going back to the temperature sensor, you would expect, okay, two cities, US cities, let's say New York and Philadelphia, within 1 hour drive, right? So you expect the precipitation of the two cities to be similar. So you have some edge weights that reflects how similar they are. So that's very reasonable. And a lot of imaging data like 2D imaging, you expect two pixels to be close to each other to have similar pixel values. So you have a positive way to describe them. But that's not the only graph you would see in practice. You would have data that have anti-correlations, right? So a clear example would be voting in the Senate in the States. Yeah? There's Republicans and Democrats. So if Democrats are voting one way, you can bet you're behind and Republicans voting the other way. So there's anti-correlations happening. So it's more appropriate to describe anti-correlations in terms of negative edge weights. So we've done work on sine graphs as well. There are also cases where you have directed graphs, right? So for example, with Twitter, popular personnel like Cristiano Ronaldo might have millions of followers, but the followers themselves might not have a lot of followers themselves. So there's a directed relationship here, or maybe it's a citation network where a paper is very well cited, but people that cite that paper is not well cited, etc. Then the relationship is not bidirectional. In this case, a directed graph might be more appropriate. So just bear in mind that different types of graphs, we actually study different kinds of graphs for different scenarios like sampling and reconstruction and so on. Let's go back to the basics. Let's assume, again, you have a empirical covariance matrix you computed from data. So you have this sigma, and you want to compute a sparse inverse covariance matrix, which eventually we're going to interpret as a graph Laplacian matrix. So this work actually is from the statistic community. They just want to compute a sparse inverse covariance matrix. So you have a likelihood term that says basically the theta here should be as close to the inverse of sigma as possible, while assuming that the theta itself should be sparse. So instead of L0 norm, you have L1 norm to promote sparsity. So you can solve this using block coordinate descent. And this is a work in statistics more than 15 years ago. Yeah, so we're going to use this as a starting point. And graph signal processing is used as a starting point and now build on that and compute the sparse inverse covariance matrix and interpret it as a graph Laplacian matrix. So You can put additional constraints. So this is the objective is quite similar to what you saw before. This is the likelihood term. It's minimum instead of maximum, but you flip the sign on the terms and it's the same. Now you constrain your reconstructed matrix, this sparse inverse covariance matrix, to be different forms of graph Laplacian matrix. So for example, it could be a configuratorial graph Laplacian matrix, which basically means the matrix has no self loops. You can have a generalized graph Laplacian matrix, which means you can include self loops. You can have diagonally dominant generalized graph Laplacian matrix, which means that the self loops in relations to the edges have a certain properties. They have to be larger than the sum of the edges, for example. So if you have a priori knowledge about what your graph Laplacian matrix look like, you can actually add a constraint and say, okay, I'm gonna learn a sparse inverse covariance matrix where the inverse covariance matrix I'm going to interpret as graph Laplacian, and I constrain Laplacian to be a certain form, then you can learn this graph Laplacian matrix for the particular application that you have these a priori knowledge. Yeah, so let me just say why is the inverse covariance matrix can be interpreted graph Laplacian matrix. So as I mentioned, the goal is to capture pairwise similarities or pairwise correlation. So the inverse covariance matrix is also called a precision matrix, can be interpreted, each edge weight can be interpreted as a conditional correlation. So that's what we want, right? We want to capture pairwise correlation or pairwise similarities. So which is why in the literature it's common to interpret the inverse covariance matrix as the graph Laplacian matrix. This is a fairly recent work we did where we make different assumption that the first k eigenvectors, for example, are known a priori. So again, depending on application, this might be reasonable. Then you can just learn the remaining n minus k eigenvectors from data using a similar formulation. So you see the objective is actually the same as the graph Laplacian that I shown 2 slides ago, but you constrain your graph Laplacian matrix that is learned. Again, basically the sparse inverse covariance matrix has to fit inside a subspace. It's actually a convex cone that shares the first k eigenvectors that are chosen a priori. So I can give you a case where this is true. For example, in image coding, the most likely signal is the constant signal. Where you look around, neighboring pixels are likely to be similar, so then the most often seen signal is the constant signal. So you can define a convex cone, which are the matrices that share the first eigenvector, which is the constant signal. You can define that, and then you can use this form to compute the remaining n minus 1 eigenvectors. This is a recent work with a colleague, Parathini, within York. So she's in the smart grid community, and she's interested in studying signals on top of smart grid. So smart grid is an example of nodes. You can think of it as a graph where you have voltages and phasors at different locations of your circuit that are related statistically. Now, the difference with smart grid compared to what I just talked about earlier is that each reading is now a complex number. Instead of a scalar, has both now imaginary and real parts. So we'll propose a technique where the graph we learn is what we call a Hermitian graph, which means that it's a directed graph where the edge weights connecting 2 nodes are in complex conjugate. So the edge weight between 1 and 2 is -1 plus 2j in one direction, in the other direction with -1 minus 2j. So having this property would mean that the adjacency matrix and the graph Laplacian matrix are both Hermitian, which by the spectral theorem means that the eigenvalues are real. What that means is that, going back to the definition of earlier, if the eigenvalues are graph frequencies, you have real graph frequencies, right? Which is convenient because you have complex eigenvalues. It's hard to interpret what you mean by complex graph frequencies. So, so the question then becomes, okay, given that we want to construct a Hermitian graph Laplacian matrix, given complex reading from your data, how do you compute the most appropriate complex graph Laplacian matrix? And so we generalize the previous technique called CLIME that use linear program to find the sparse inverse covariance matrix to the case when you're dealing with complex signals. So this is a paper we just recently submitted to SmartGridCon. So what are the applications of graph learning? So again, actually, graph learning is the starting point of any graph signal processing. You have to argue for an appropriate graph that captures pairwise similarity before you start. So I'm just going to give a very simple example of image coding. This was a paper last year in ISIP. Just to give you a background on what image coding, how does transform coding work in image coding? So basically in JPEG, you would divide an image into 8x8 blocks, pixel blocks. And then for each block, you would do a DCT transform, discrete cosine transform, essentially to sparsify your signal, right? So that the number of non-zero coefficients are few. And then you just encode those because instead of 64 coefficients, you're only encoding like 4 or 5. That would give you a compact representation, and that's how you would get good compression. The question is, well, DCT is fixed. If the statistics of your signal actually changes over time, how do you know you're doing the best compression possible? So instead of DCT, there are works that KLT is basically a transform that is computed in real time, looking at the inverse covariance matrix, doing the eigen decomposition, and that would give you a sparse representation of your signal. The problem with that is that there are too many parameters to compute. So if you have an image that statistics vary quite quickly, it's difficult to capture all the statistics in real time. So the idea here is to use our graph learning methodology that I mentioned a couple of slides ago, and assume you know the first k eigenvectors that you would know, for example, from experience. As I mentioned, for example, the first eigenvector can be constant regardless of data. Then you will learn the remaining n minus k eigenvectors from data, so that the parameterization of your transform is not as large. You don't have to learn as many parameters, which gives you a more stable transform for compression. And experimental results bear that out, that if you're able to tune this k, basically take k control how many parameters you need to learn from data, you can vary your compression efficiency. So let's move on for graph learning to graph filtering. So now we assume, let's suppose you have a graph and you want to do some processing of the data on top of your graph. It could be things like denoising. Denoising is one of the simplest, the most straightforward inverse problem, restoration problem. So you assume the desired signal X is corrupted by some additive noise Z. You only observe the noisy version, which is why you want to recover X as much as possible, right? So you can formulate maximum posteriori formulation and say, hey, I want to recover X so that it's close to my noisy observation Y. So that's your fidelity term, that's the L2 norm. Now you need an additional signal prior, right? You need some prior knowledge about your signal to help you recover your signal. And in this case, we can propose graph Laplacian regularization. Basically, assuming I can construct an appropriate graph that captures pairwise similarity, I want to construct a signal X that is consistent with my graph. But what does that mean? That means that if the edge weight is large, you're minimizing, right? So you want this X transpose Lx to be small, right? So if the edge weight is large, then the expectation is that I and J are similar, right? If you have a large edge weight, then you would expect Xi minus Xj squared to be small, right? Because you're minimizing, so if this is large, this must be small, right? If Wij is actually small, then well, Xi and Xj could be, because there's no expectation for them to be similar. So minimizing this X transpose Lx from the nodal domain, you're saying, hey, I want a signal that is smooth with respect to the graph. Again, that means that for large edge weight, you expect Xi and Xj to be similar. Actually, there's a spectral interpretation as well. If you look at X tilde K, that's the K Fourier transform coefficient of the signal. Right? Remember, we can decompose L into a set of eigenvectors and eigenvalues. So if you compute the coefficients by doing the inner product of the signal with respect to each of the eigenvectors, you get these coefficients, these graph Fourier transform coefficients. And so you have a small X transpose Lx. Basically, you're saying that the energy must be squeezed to the coefficients associated with the low frequencies, right? Because you're scaling by the lambda k, which are the graph frequencies. But what does that mean? Do you squeeze all the energy to the low frequency components? That means you have a low pass signal or a smooth signal. So minimizing this X transpose Lx has a good interpretation both in the nodal domain and in the graph frequency domain. Now, if you look at this equation, you're minimizing L2 norm and L2 norm. This is easy, right? This quadratic programming unconstrained version. So you take the derivative with respect to X, you set it equal to 0, you get the set of linear equations, and you can actually solve for this efficiently, assuming that the coefficient matrix is sparse, positive, definite, and symmetric. So I'll come back to this equation a little bit later, but I just want to point out exactly what is this saying, right? So you can actually compute X by computing this matrix inverse. Again, in practice, you won't do the inverse because it's order n cubed, but for the sake of interpretation, suppose we do, then this inverse matrix is a linear operator. It's another matrix, right? So you basically compute this thing X star by having a matrix vector multiplication, right? So basically the solution to this optimization problem is a linear filter. Yeah, so that's the first interpretation. Second, you can expand out this term, this matrix inverse, into this form, again, by remembering that L can be decomposed into its eigenvector V and then the eigenvalues, the diagonal matrix that contains eigenvalue and then V transpose. Then you can expand this into this form. And what is this saying? This is basically saying the input signal Y, you do the graph Fourier transform to its coefficient. Each coefficient is now scaled by 1 over 1 plus mu lambda k, and then you would convert it back into the nodal domain. So in the spectral domain, in the frequency domain, each coefficient is being scaled by 1 over 1 plus mu lambda. So if lambda is large, you have a large denominator, you're squeezing the high frequency. So this is actually a low pass filter. Yeah, because you're converting it to frequency domain, you're scaling the coefficients corresponding to its frequency, but high frequencies is attenuated more than the low frequencies. And therefore it's a low pass filter, which is reasonable, right? Because you remember that the X transpose Lx, the prior is trying to promote low frequency reconstruction of the signal anyway. So the fact that this, again, this linear filter is actually a low pass filter is not surprising. You might be wondering, how do we construct the appropriate graph that captures the pairwise similarities? And there are many ways of doing this, and that's one of the key point in graph signal processing, how do we construct a graph a priori to capture pairwise similarities. But there's actually a lot of literature that talks about this. So for example, this is if you have background in computer vision, you might recognize you can do a bilateral filter weights, where between 2 pixels, you would say, well, the 2 pixels are close in distance, in location of the image, you would like a large weight. And if the observed pixel intensities are similar, you also want a large weight. If you do that, that's called a bilateral filter weights. And based on these weights, you can construct a Laplacian matrix, and then you can do the filtering, as I mentioned. This also means that because the reconstructed signal is X, but the weight is also a function of X, then actually you can think of this as a signal-dependent graph Laplacian matrix, and you can actually solve this multiple times, right? So you do a filtering of your graph filtering of your signal based on this equation. You have a new estimate of your pixel values, X. You update your weights. You do another filtering, et cetera, et cetera. This would actually promote piecewise smoothness, like a total variation. So this is proven in some of the other papers. And actually doing something quite simple, right? You're just doing a minimization of 2 L2 norms. Iteratively, you can actually get pretty good image reconstruction already. So this is a paper I wrote with one of my previous students 6 years ago. You can see, so this is not comparing with deep learning methods, but compared to the classical denoising methods, we actually do quite well. In particular, you can look at the tablecloth where you actually have piecewise constant type texture. We reproduce the signal quite well. And for actual piecewise constant or piecewise smooth signal, like the depth images, we are, at that point at least, we're state of the art in terms of reconstruction. And this can be extended to things that are beyond imaging. So with my postdoc, we'll look at things like a point cloud, denoising. In this case, the trick here is that when you construct a similarity graph between 2 points in 3D space, we use more than just location. We use actually surface normals, estimated surface normals on a 3D point to compute edge weights between neighboring nodes. So using that similarity graph and some tricks on graph filtering, we can do a pretty good job in terms of point cloud denoising. You can do similar tricks for point cloud super resolution. So in this case, we assume that the input point cloud is not dense enough. You want to increase the number of point count within your point cloud. So how do you increase the density of your points? So this is point cloud super resolution. We've done it for the case of video. So in the case of video, you actually consider the consistency between neighboring frames as well. So we've done that. Some more visuals, you can see that our reconstruction is better than some of the competing schemes. Another example here. This is our approach. This is competing schemes. So that's graph sampling. So let's talk a little bit about graph filtering. Let's talk about graph sampling. Again, going back to your undergraduate signal processing course, we talk about sampling a band-limited signal, right? Everybody remember that? We talk about Nyquist sampling frequency. If a signal is band-limited to some frequency f, if you sample it twice the frequencies, then you guarantee reconstruct your signal without loss. Yeah, so that's essentially like the sampling frequency. And the reason we have such a clean result is because the kernel is regular, right? So you bound the frequencies of your signal is band limited, so you cannot have variation faster than a certain amount. Then you would know how fast you need to sample to reconstruct your signal. So that's very reasonable, right? So now you want to extend the notion of sampling from regular kernel to irregular kernel. What changed? Well, what changed is the fact that the value of each sample is now different because the kernel is now different. So for example, you look at a node here, right? It has 1, 2, let's look at a node, yeah, here, 1, 2, 3, 4. There's 4 neighbors here, yeah? So you compare this node to a node here, which has 2 neighbors. Which one do you think is more valuable? Obviously the first one, right? First one, because you have no more neighbors. So you have a sample here, because the graph tells you that it's similar to these other neighbors as well. You would know information about 4 other neighbors. Whereas if you only know a sample here, because there's only 2 edges, you would know some information about 2 connected neighbors. So the point here is that because the value of each sample is now uneven, they're not the same. When you do sampling on graphs, not only do you need to specify how many samples you need, but where you place your samples. That's kind of the key challenge here. You still make some assumptions about the smoothness of your signal that my signal won't change across my graph kernel by a certain amount. It's still going to be slowly varying to some extent. But then you need to specify where you place your samples. Yeah, so there's a lot of work on graph sampling within the literature, and they would make similar assumptions. I mentioned you can have a band limited assumption, basically say for a given definition of graph frequencies, the signal is band limited, so it won't have any high graph frequencies. So all the energy beyond a certain threshold will be all 0. So that's one way of making an assumption for sampling. You can also assume that the signal has small X transpose X. That's the measure of signal variation on graphs, as I mentioned earlier. For directed graph, it's more complicated, so I'll leave that for now. Yeah, so what I want to talk about next is how can you do fast graph sampling? So as I mentioned, you can make these assumptions about smoothness, graph smoothness with respect to graph frequencies, but the graph frequencies are eigenvectors of a variation operator like graph Laplacian matrix, which, as I mentioned, a full eigendecomposition is order n cubed. So that's not very scalable. So recently there's a lot of development on eigendecomposition free sampling. So can I tell you where to place my select nodes for sampling without doing any eigendecomposition? And that's the direction I want to briefly talk about. How can we do graph sampling without any eigendecomposition? So I'll just briefly overview our general approach. There's a paper we published in TSP in 2020 that goes into a lot more detail. We're going to start from the reconstruction. So given a set of samples, so Y is a set of samples, let's say this of length, I think, M. So suppose you have M samples from the original signal, which is length N. So N, you have the number of nodes. M is the number of samples that you collected from your chosen M nodes. So let's assume they're related as HX plus V, where V is some kind of additive noise. then you can say, well, I want to reconstruct my original signals from my samples by minimizing an objective where the fidelity term says X, after I do a sampling using sampling matrix, H should be similar to my observed sample, which is Y. So you have an L2 norm, very similar to the denoising objective that we saw earlier, right? Before it was Y minus X, now it's Y minus HX. They're both L2 norm. And I want my signal X to be smooth with respect to the graph. So using the same GLR as regularization. Again, this is a L2 norm minimization problem. You take the derivative with respect to X, you get a system of linear equations, and you can reconstruct your signal from your samples as you see here by solving the system of linear equation. But what I want to focus on is not so much the reconstruction, but the coefficient matrix, which is this H transpose H plus mu L. So it turns out this matrix, it's very important in terms of deciding our sampling objective. This coefficient matrix H would determine the stability of your reconstruction signal. In particular, the conditioning number is bad, which is the ratio of lambda max or lambda min of this coefficient matrix, then your signal reconstruction won't be stable. So to make the conditioning number stable, what we want to do is maximize lambda min of this condition of this coefficient matrix, which is called the E optimality criteria. So E here actually stands for eigenvalue. Like, we're trying to maximize the lambda min of the coefficient matrix. That's why it's E, it's the eigenvalue of the coefficient matrix. Another way of motivating this objective is to say this lambda min of B, the one that we're trying to maximize, actually is related to the worst case reconstruction error of your signal, as you see here. So maximizing lambda min actually would also mean minimizing the worst case reconstruction error. So how do we select sampling matrix H to maximize this lambda min of B, of this coefficient matrix? I'll give you some intuition without going to a lot of math. So basically what we want to do, instead of maximizing lambda min of B, we're going to maximize the lower bound of lambda min of B using Gershgoin-Circles theorem. So a very quick review of what is Gershgoin-Circles theorem. This is essentially a way of telling you about the eigen properties of a matrix without doing eigen decomposition. In particular, we're going to use this to derive a lower bound of lambda min. So suppose you have a matrix here, 3x3 matrix, with diagonal entries and off-diagonal entries, right? For each row, I'm going to construct a Gershgoin disk where the center is located at the diagonal entry. So the first row has diagonal entry 2, so the center of the disk is 2, okay? And then the radius of this Gershgoin disk is the off-diagonal terms in absolute value, right? So it's your -2 and -1. So the sum of the off-diagonal terms in absolute value is 3. So you can see that there's a disk here, center at 2 with radius 3. So that's the Gershgoin disk corresponding to the first row. And you can do the same for the second and the third row. Okay, so these are the three Gershgoin disks. And Gershgoin-Circles theorem tells you that each eigenvalue of the matrix must live inside at least one Gershgoin disk. Okay. What that means, the corollary of that is that the smallest Gershgoin disk left n must be a lower bound for lambda min, right? Because if lambda min is actually somewhere here that is smaller than the Gershgoin disk left n, then there's no disk that actually covered that value, right? So it cannot be true. So the Gershgoin disk left n is actually a lower bound of your lambda min of your matrix. And you can see again the power of Gershgoin-Circles theorem at play here. You can compute a lower bound of lambda min without doing any eigen decomposition, computing any eigenvectors, eigenvalues, right? It just gives you a lower bound just by looking at the entries of your matrix and computing some addition, right, an absolute value, right? So that's cool. You can compute a lower bound of a matrix without doing any eigen decomposition for lambda min, but it's actually not often used, right? This smallest Gershgoin disk left n as a lower bound for lambda min. Why? It's because the bound is usually loose. So for example, you can see this matrix here is actually positive semi-definite, but the smallest Gershgoin disk left n is actually at -1, right? So the difference between the minus lambda min lower bound and the actual lambda min can be quite large. So that's not very useful in this current form. So what we do is we do a similarity transform. So you pre and post multiply by the matrix, the coefficient matrix P, by an invertible matrix S, then the similarity transform of the matrix preserve all the eigenvalues. So they have the same eigenvalues. Then the lower bound of the similarity transform would also be a lower bound of the original matrix. And actually with the careful selection of S, you can tighten the bound. In fact, we've proven in the paper that the bound can be infinitely tight for certain type of matrices. So how do we use this to, going back to the problem that I want, which is choose the sampling matrix that maximize lower bound of lambda min. So basically we do what we call Gershwin graph sampling. The idea is to shift and scale the Gershwin disk by the sampling matrix. I'll walk you through a very simple example, then I have to move on. So if let's say I have a line graph, 1, 2, 3, 4, and I select node 3 as my first sample, right? When I select node 3, you look at the coefficient matrix, that means that the third diagonal entry of X transpose H becomes a 1 from 0, right? So because the diagonal entry is now increased by 1, the Gershwin disk will move to the right by 1, as you can see here. Now, if I choose the similarity transform, this S to be a diagonal matrix, I can scale basically the entries within the third row and make it smaller. So, make it larger. So I'm basically increasing the radius of the Gershwin disk 3. But in so doing, because of the S inverse, I'm also shrinking the radius of my connected nodes. So in this case, it will be 2 and 4. And so the 2 and 4 Gershwin disk this radius would shrink. And you can see that through this process, after I pay a price to sample this node, which shifted this to the right, which is good. I'm trying to move the smallest Gershwin disk left hand to the right, right? So moving any disk to the right is good. But after I move it, I can do some expansion of the radius and shrinking of its neighboring disk so that everything get adjusted. So everything get moved to the right a little bit. Yeah, so that's how I would maximize the Gershwin disk left hand. So the way I explained it in the workshop last week, 2 weeks ago, is that like if you have kids at home, you've bought this like silly putty, like you push one end, something else pop up. That's essentially what we're doing here. We're trying to maximize the smallest Gershwin disk left hands, right? So we pay a price to shift something to the right. Now we're playing with this silly putty to adjust the left end, so the furthest left end get all pushed up to the right as much as possible. So eventually, for the right set of matrices, all the left ends would all get pushed to the right end. It'd be like a city putty that all the ends get lined up to the same value, and that's kind of the best you can do. So without going into the details, that's kind of the main idea of what we're doing here. Again, we're doing all these things without computing any eigenvalues or eigenvectors. So we're just trying to maximize the Gershwin disk left ends. So because we're not doing eigendecomposition, we can show that our sampling algorithm is actually quite fast compared to existing work. So skip that. This is just to show that if you have a community graph, you would expect the samples to be picking from each community, right? Because they have a lot of similarity within each community. And you can see that from the results, we are actually doing that. So that agrees with our intuition. We can extend this to sign graphs, so I won't go into details of that. Again, this shows that in terms of mean square, we're doing well. We actually, for speed, we're also doing well. This is the recent result we got from our ICAST paper 2 weeks ago. So for directed graph, we can do something similar as well using some mathematical tricks. Again, in terms of both speed and reconstruction, we do quite well relative to existing work. Some interesting applications of working with a multimedia expert in Taiwan. You can actually model. This is the case when you do video summarization. You want to extract keyframes from a video. So let's say somebody upload a 3-minute video to TikTok or YouTube. You want to summarize the video with 10 frames. Let's say I can afford 10 frames. What are the 10 keyframes? You can model the frames to frame similarly using feature distance, using GoogleNet, for example, for extracting features. And then once you have this similarity graph that tells you how different frames are related in terms of similarity, you can use our algorithm to select frames right? Again, you have a whole bunch of frames that are really similar, you only select one, right? Then you scroll on to the next batch. So modeling the keyframe selection as a graph sampling algorithm actually makes a lot of sense. Again, our key advantage here is that we can do everything in linear time. You can do this with matrix, actually not matrix completion, but sampling for matrix completion. So imagine you have a Netflix problem, you want to know which user liked which movie, but you can only query a fixed number of people about what movies to like. So how do I select samples for matrix completion? So this is a sampling for matrix completion. If you have a user graph that tells you how users are similar, you have a movie graph that tells you how movies are similar, using this product graph that tells you how movies and users are similar, you can actually do a sampling algorithm and select queries so that you can reconstruct the matrix. You can also do 3D point cloud sampling. So this is the opposite direction, right? We're not doing super resolution. We're saying that if you want to represent a point cloud using very few samples, which point do you want to choose to represent your original signal? So we've done that as well. So last, I want to present some results about how GSP analysis can inform you to design graph convolutional nets better. Again, some of the key insights that hopefully I bring forth today is that looking at the spectral aspect of the graph is informative. And that's what we're trying to do here, is to, using insights we learned from the spectral aspect, inform better constructions of graph convolutional nets. The first work is actually in collaboration with an industrial partner in the States. This is a company, Growers Edge in Iowa. They're interested in crop yields prediction. So they actually, in the state of Iowa, this is the different counties within the state of Iowa. They in the corn belt, so they grow a lot of corn. And they want to predict what the corn production will be for the following year so they can make the right financial package for farmers. Obviously, you make a correct or more accurate prediction, then you have to have a lower risk and they can offer a better financial package for the local farmers, right? So crop yield prediction is is an important problem for them. And you can see how graph can play a role here, right? Because you have two neighboring counties, likely they will have similar environmental variable in terms of soil composition, precipitation, sunlight, etc. And so you can model the crop yields of neighboring counties with an edge weight that reflects the pairwise similarities. And using this graph, you can actually do prediction, and people have used graph convolutional nets for that before. We're working on that also. But how dense of a graph do you want? So there's a trade-off here in the sense that, well, if you want to have pairwise similarities, you can have n square edges, right? But then learning a very dense graph is computationally expensive. It may not be really worthwhile. So you want to sparsify your graph to lower training execution time. What's the best way of lowering how to sparsify a graph? So our technique is actually very, very simple. We're looking at the second eigenvalue, which is called the Fiedler number. So the second eigenvalue at a high level measure the connectedness of the underlying graph. So for example, if a complete graph all weights 1, then the Fiedler number, I think it's n-1. And if the graph is disconnected, the Fiedler number is 0. So basically the second eigenvalue is a measure of how connected your graph is, right? So you want to sparsify your graph, you want to sparsify in a way that does not harm the connectedness of the graph. And so one way of doing that is to say, well, I want to remove an edge each time. That makes the smallest change to my second eigenvalue, right, from a dense graph. But that would be expensive because you need to test out each candidate and compute the second eigenvalue. So we actually can leverage on a perturbation, eigenvalue perturbation theorem that tells you that a new eigenvalue is the previous eigenvalue plus or minus a range, where the range is the change with the perturbation matrix multiplied by this second eigenvector. Yeah, so depending on which edge you want to change, you have a different perturbation matrix. And if the L2 norm of this matrix vector multiplication is small, that's the edge that we want to pick, because that would make the smallest change with the previous Fiedler number. So this turns out to be quite efficient and leads to fast sparsification of your graph without harming the prediction of your crop yields. So there's some, I won't go through the details, there's some results here and then it's explained in this paper. There's also an observation that for graph convolutional nets, you cannot go too deep. If you go too deep, it would become over smooth and the results is now uninformative. So this is observed in multiple papers. And there's a landmark paper from the University of Tokyo that talk about what exactly is happening mathematically. So basically what's happening is that as you do each layer in your graph convolutional net, you are getting closer and closer to a subspace spanned by the first eigenvectors. And the rate, if you totally project it onto this subspace spanned by the first eigenvector of the Laplacian matrix, then it becomes uninformative, and the rate in which it converts to the subspace is affected by the distribution of your eigenvalues, the spectrum of your graph Laplacian matrix. So again, without going into a lot of details, then going back to the first point I was talking about, if you want to learn a graph, then yes, you want to capture pairwise similarities, but you want to do it, you can do it in such a way that you slow down this over-smoothing, right? Again, the over-smoothing effect, this convergence of the subspace spanned by the first eigenvectors is affected by the spectrum, then you can manipulate your spectrum in such a way that you slow down the rate in which it converges this subspace spanned by the first eigenvector. So it's essentially a sparse graph learning technique with a spectrum prior to slow down over-smoothing. So it turns out that is quite effective in terms of performance. And so what is shown here basically is that using the spectrum prior, you can learn a graph so that you have more layers and that you have a smaller mean square error as well. So you basically slow down the over-smoothing process. I'm just in time, so I'll just conclude here. So hopefully I give you a reasonable overview of what graph signal processing about. It's about processing of signals, discrete signals on irregular kernel described by graphs. What is a graph? Graph hopefully will be capturing pairwise similarities, pairwise dissimilarities, or even cause and effect in the case of directed graphs. There are different topics within GSP that are quite interesting. Graph learning, again, you need to learn the appropriate graph from data before you can do anything else. There's filtering, sampling, and then the spectral knowledge analysis that you would get can inform better graph convolutional nets as well. I've listed a bunch of applications that we're studying within my group, and you can see GSP has a lot of different applications. I'm always delighted to work with different colleagues within the department. Currently, I work with, I mentioned, Parathini on smart grid. I'm working with Professor Andrew Eckford on neuroscience topics. We're doing ganglion cell firing. We just submitted a paper to GlobeCom, working with Michael Brown on joint image denoising and interpolation. So feel free to drop me an email, look at my homepage. A lot of my publications can be available there. We have a new book, not so new actually, 2 years ago, that talks about graph spectral image processing. So please buy books and get some royalties. Thank you.
Would you like me to record the questions? Or?
Sure, why not? Any questions from the audience?
If we go back to the paper, the smart grid paper with Dr.
Sure.
I believe that for that paper, your sampling was n square. Am I right? Because you consider all nodes.
So, so this paper, we're not talking about sampling. So here we actually talk about interpolation. So in this case, we assume we learn a graph first, in this case, a Hermitian graph, after which we do estimation of the states that are missing. So we're actually doing interpolation, not sampling here.
Okay. Well, because my question was like, in case like that, with a bigger network, and I have n squared.
And square what? So the n is number of nodes, right?
Number of nodes, so my matrix would be n squared. Like my sampling would be n squared because I'm sampling in all nodes.
It's still order n, right?
Sorry?
Why is it n squared? You have n nodes, you can order n, right? Like why is it n
because
squared?
the Y matrix, the one that you have, they have L.
The
Oh,
L
yeah.
doesn't have to be dense, though, right? L doesn't have to be dense. L is usually sparse. So you learn a sparse matrix from day one, right?
Okay,
Yeah, we almost never use a dense matrix. Yeah, because we want to have algorithm that are linear time.
okay. Then my question was, if I have this huge matrix, I want to simplify this matrix by ignoring some nodes that I would assume that I will find equivalent for certain node, just to simplify it.
I suppose you can prove nodes, but again, the typical technique is to learn a sparse graph from day one, right? So actually everything I talked about so far about graph learning, we emphasize on sparse graphs. The matrix, Laplacian matrix is almost never dense. It's always order n number of non-zero entries within the Laplacian matrix.
Thanks, Gene. Really nice talk. It's very far afield from the sort of work I do, but I couldn't help but think of some similarities and possibilities. In your last slide, I was just looking under applications to see if there was anything under pattern recognition or identification. I didn't see anything there, but I'm just wondering if there are possibilities in terms of pattern recognition, pattern matching, that sort of thing. I'll tell you why I'm asking in a second, but first of all, are there applications for pattern matching, pattern identification, that sort of thing?
Yeah, indeed there is. So actually a lot of my colleagues are looking for things like anomaly detection. So you learn the normal behavior from statistics, then the normal behavior would appear at low graph frequencies, right? Then when you have abnormally, let's say there's a adversarial attack, they would usually appear at high graph frequencies.
Okay,
So that would be one way of using graph signal processing for that.
so let me follow up with why I was asking this question. One of the areas I work in is handwriting recognition. And one of the methods that's quite widely used today is often called shape writing, where you, on a keyboard, you just, the graph is just a pattern of letters in a word on a keyboard. And what you have is many tens of thousands of reference graphs, which is basically a dictionary of words and the pattern for each word. And then you have a sample graph, which is something that the user did. And the goal is to find the closest match of the sample, the user's graph, with the dictionary of graphs representing, many tens of thousands of words in a dictionary. Is there anything that you are talking about today that would have an application for that type of an application?
I think it might. Again, I think if you learn from all these graphs, there might be some commonality you can draw, and that will become low graph frequencies on the representation graph. So
maybe. So one of the bits of information in the graphs I'm talking about is that the nodes, which are basically letters, keys on a keyboard, become nodes. The order of the nodes is important. It's not just the existence of the nodes, they occur in a time sequence. So if the word is hello, it's HELLO. You know what I mean? So that's an additional level of information that's available.
right, so that will become a directed graph, right?
Yeah.
So it's possible. I think I need to sit down and think about it. But yeah, I think it's possible.
Okay, I'm just gonna map what you're talking about to what I think. So thank you.
Any other questions from the audience?
I have maybe a very, my question is not very well formulated, but what we do is we do some printed electronics and we try to use the photos that we take, some sort of image recognition, maybe some image processing to basically optimize the settings of the printing. And can we use this to match basically the photos that we take to the printing settings and maybe try to estimate which printing settings would work better? Kind of like maybe a machine learning situation? Or with,
Right, so I would need to know a little bit more specific, but potentially,
yeah,
yeah,
okay.
you can probably formulate like a bipartite graph,
Okay, maybe we can
right?
discuss.
Yeah, yeah, we can talk offline. That could be interesting.
Yeah.
Any other questions?
Okay. Okay, I guess we can just thank Professor Jean.